Good evening, everyone. I'm Joshua Wolabi Adeleke, and with me is Madi Ibrahim Mensa. We are PhD students in the Department of Applied Mathematics here at Illinois Tech. And today we will talk about a very influential paper by Jordan, by Kendalier, and Otto titled The Variational Formulation of the Fokker-Planck Equation. And we know that this work is one of the foundations of the now very rich connection between partial differential equations, probability theory, and optimal transport. And our main goal in this presentation is to explain how the Fokker-Planck equation, which at first sight is just a diffusion drift PD, can be reinterpreted as a gradient flow of a free energy functional in the Wasserstein space of probability measures. So now Madi is going to take us through from the introduction to the uniqueness argument part. Thank you. Madi, over to you.
Great. So, like Josh rightly said, the Fokker-Planck equation described the time evolution of some process and some density. And it's a PD, and it is associated with some stochastic differential equation. What is profound and insightful in JKO's paper is the fact that they viewed this problem as a variational problem, in the sense that they turned the problem into an optimization problem where they considered some functional, and then they saw that the functional decays with time. And so through some variational methods, we're able to extract the PDE. And so the goal here is to, first of all, identify what such a functional is. And here we have that the free energy functional, which can be associated with this particular Fokker-Planck equation, is defined as the sum of some energy and a entropy term. So the energy term is basically some potential, and the entropy term is root log rho, as we all know. So this is actually the negation of entropy. And as we take time to infinity, what we notice is that the Fokker-Planck equation would have some assumptions. The Gibbs measure as solution. Now, what we want to do is to, first of all, see the sense in which all this is possible. So we consider the gradient flow of this functional, and that is to take the time derivative of the free energy functional and see if it is indeed negative. But in what sense are we doing this? And this was actually like a key insight in their paper, to be able to observe that the sense in which we are taking the gradient is not the usual L2 norm, but rather the Wasserstein norm or metric. And so when we take the time derivative of this functional, what we observe is that it can be defined as the negation of the squared norm of the Wasserstein 2 metric. This indicates that, one, the Fokker-Planck is decaying with time, and it is decaying with the steepest decay of this functional. And two, the sense in which this is possible is through the Wasserstein metric. And it explains actually why we get the Gibbs measure as a solution. So here we have the Wasserstein metric defined. That is the sense in which we are able to transport densities from one measure to the other. And it is the most optimal way of transporting density. That is, we consider the infimum of all possible ways in which we can transport the density from mu to nu with some cost associated. And here the cost in question is the quadratic cost of the displacement. And so what they did was to take the space of densities and then equip it with this Wasserstein metric, and they got a metric space out of it. And this Wasserstein metric actually gave them the geometry required to be able to define the flow of the gradient of the functional. So here we have the the admissible sets of densities, and they are the sets of densities in which their second moments are finite. And this ensures that the Wasserstein metric is indeed finite, and that the free energy is also well defined, ensuring tightness for compactness argument. So the scheme which they defined, having gotten this this geometry, what is the scheme that they were able to come up with? And the scheme is defined such that we look at any time step, we look at the possible row which minimizes the functional, but at the same time stay close to the previous row. So with this notion, we see right away that we are actually trying to find a balance between the Wasserstein metric and then minimizing the functional in a sense. And so this is what they did, and to be able to actually show that there exists a minimizer for this scheme, we need to go through a few series of steps. And the main things to check is the coercivity argument and then lower semi-continuity argument. The coercivity argument is checked by ensuring that the second moment are well bounded under some minimizing sequence, and then through uniform boundedness of the Wasserstein metric and the second moment, they were able to show tightness of this minimizing sequence, and then with Prohorov's theorem, show that there is actually some weak subsequence that converges weakly to rho at each time step. So the estimates that they derive from the lower side of entropy, or the negative side of entropy, is given by this bound. And it can be made sharper if you assume that we are using the Gaussian measure. So with this, we had coercivity established, and lower semi-continuity can be established through Fato's lemma for the potential. Because the potential are all non-negative, we are able to establish that it is lower semi-continuous by considering Fato's lemma. The next thing is to show that the Wasserstein metric is also lower semi-continuous, and that can be checked through some convergence argument and the fact that the functional, the metric actually is also convex. It's a convex functional. So combining those, we get that indeed our objective is lower semi-continuous. Together, the lower semi-continuity and the coercivity argument establishes the existence of a minimizer for this discrete variational scheme that they constructed. The last thing one would want to check is if indeed the derived minimizer is unique. And to check uniqueness, we check the set of admissibles, and yes, it is convex. Also, the free energy functional is strictly convex via the entropy term. And the last thing to check is the Wasserstein metric, which is convex in the geodesic sense. So that establishes the uniqueness of the minimizer at each time step of the variational scheme. So, Josh, please take over for the
Thank you,
continuity.
Maddie.
No problem.
Thank you, Maddie. Can you stop sharing your screen?
Sure.
Can you see my screen?
Yeah, I can see now.
Okay, yeah, so thank you very much. So in the remaining slides, we will outline the main ideas that go into the convergence proof, that is the discrete Euler-Lagrange equation, the compactness, and the passage to the limit. So here, to the first thing first want to check is to derive the Euler-Lagrange equation at a fixed time step k, as Maddie has outlined earlier. So we consider smooth perturbation of the minimizer, that is rho superscript k, and we let eta be a smooth compactly supported vector field. Eta here, as we can see, is a compactly supported vector field, and then define a flow, which is what we have here, P subscript style, by solving this equation here. And then we push forward the density, which is what we have here. And by optimality, the function, I mean, with respect tau, tau should return j over tau should be an input, and it should give us j of rho subscript tau. So we expect, I mean, by optimality, the function tau, which gives us j of rho subscript tau as a minimum at tau equals to 0. So its derivative at 0 must vanish. So, and computing the derivative of the free energy, what we have here, along this flow gives this equation that we have here, and this expresses the first variation of the free energy in the direction of the vector field, which we have here, which is eta. So now the more subtle part is the variation of the Wasserstein term, and here they assume that there is an optimal transport, which is T subscript k that we have here that pushes this, the rho superscript k, forward to this, that is rho superscript k minus 1. So, and then the squared Wasserstein distance can be written as W superscript 2 and subscript 2. We have it defined in our report, but not here. So using a perturbation by the flow, that is P subscript tau. So JKO did show this, what's it called, relation here, and combining the variations of our, what's it called, of calligraphic F, which is the free energy, right? Which is the free energy in there. We would see that, I mean, combining the variation of the free energy and the Wasserstein time, and using the fact that the derivative of J of rho subscript tau at tau equals to 0 must vanish, we obtain this relation that we have here, that is negative 1 over tau, and the rest here in a weak sense, rho superscript k almost everywhere. And this motivates the discrete velocity field that we have here, that is v subscript k of x. And the identity becomes what we have here. And so the optimal map and the flow structure are tightly coupled, and that is the discrete velocity points in the direction of the negative gradient of the free energy. So here, the optimal transport relation can be written as a discrete continuity equation, that is for any test function phi that we have here. We have this expression or this equation, and expanding this alone, that is phi of t subscript k of x to the first order in tau, and rearranging times yields formally some relation which we didn't include there. That is, we just have to take the integral of this and we multiply with phi, then plus what we have here, but not the exact form anyway. It's going to be the grad of phi, then dot v subscript k of x, then rho superscript k of x dx. And so, and after, and this is actually the discrete analog, I mean, the one we didn't write out here, so which you will finally see in our report. So this is actually the discrete analog of the weak formulation of a continuity equation. And if we substitute this, that is v subscript k in there, we obtain precisely a backward Euler discretization of partial T of rho, which is equals to the divergence of rho grad psi plus the Laplacian of rho. So in the limit t as t goes to 0, the discrete curve, that is rho subscript tau of t, solves the Fokker-Planck equation in the weak sense. And now for the compactness argument, that is to rigorously pass to the limit, JKO use energy dissipation and the compactness argument, that is from the minimizing properties of rho superscript k, one can derive an energy dissipation inequality, which we have here, that is a summation from 1 to k of the Wasserstein metric plus the rest that we have there. And this in fact shows that the free energy is non-increasing and that the accumulated metric speed is controlled. So together with the second moment bounds, this allowed the use of the Ascoli type theorem in the Wasserstein space. That is, one extract a subsequence, that is rho superscript tau superscript g of t, that converges to some limit rho of t in a suitable sense. So finally, one takes the limit in the derivative in the discrete weak formulation involving test functions phi of t of x, and recovers the weak formulation of the Fokker-Planck equation and uniqueness of solution in the considered class, then shows that the whole sequence converge, not only a subsequence. So, and this is the details in here from here. So now we then considered a few examples. That is, we tried to make the abstract theory more concrete, and we chose to mention two classical examples where the JKO scheme reproduces well-known PDE. So the first case happens to be a pure diffusion case. That is, if C equals to 0, then the Fokker-Planck equation reduces to partial T of rho equals to Laplacian of rho, which is the heat equation that we know of, right? And then the free energy is just the entropy, and the JKO scheme becomes a variational formulation of the heat flow as a gradient flow of the entropy in Wasserstein space. Another example we consider happens to be a quadratic potential, which that is, we consider our C to be equals to half of absolute value of x squared, and the associated Fokker-Planck equation is the OU process, the Austin-Uhlenbeck process. So, and that is a stationary solution is a Gaussian, and the JKO scheme captures the exponential convergence of rho of t towards this Gaussian in Wasserstein space. So, I mean, the question you might want to ask is that why this example? So this example illustrates how same variational structure can accommodate both pure diffusion and drift diffusion in unifying framework. So in conclusion, let me briefly summarize the main points. We looked at the Fokker-Planck equation, which can be rigorously interpreted as the gradient flow of the free energy functional, calligraphic F in free energy functional in the Wasserstein space of probability measures. We also looked at the JKO scheme, how it provides a time discrete variational formulation, whereby each step is an optimization problem, balancing transport cost and energy decay. And we also consider the existence and uniqueness of each step, which follow from coercivity and the lower semi-continuity argument in the space of probability measures. And lastly, we consider the convergence of the scheme, how the convergence of the scheme uses the Euler-Lagrange identities and the metric compactness and energy dissipation to show that the discrete dynamics approximate the continuous PD. So at this point, we would say that in our report, we focused on reconstructing the core argument of the original JKO paper in detail. So because in here we skip some details, or we can find some of those details in our report. And I will say thank you very much for your attention. So yeah, on the final slides, we list the primary references for this talk. So in our written reports, we cited related works by Brenian, Gambo, and others, which expand the theory of optimal transport and gradient flow in metric space. Thank you, and thank you indeed.